2009.
Yeah, way back then. Well, welcome everybody. Sorry, we were wrestling with a bit of a technical issue there, as we have been the last few months. But I think the flight officer has things in hand now, so I think we're good to go. We have a really packed meeting. In fact, Chris and I were losing a little sleep around this in the last couple of days when we were trying to put our slides together, because I think previously our record for slides for one meeting was 140, and tonight we have over 200. So
we like 100.
Yeah, we like 100. I had originally put out an email saying to folks, you know, if you've got Venus Transit slides that you'd like to share, send them on by, and it was like I'd opened the gates of hell. It was like, anyway. So, but that being said, I have to apologize to a couple of folks who may or may not be here, because we had to seriously bump around our presentations as well. There were a couple of presentations that were slated that we're just not going to be able to get to. I don't know if Jim is here.
Jim's here.
Jim is here. Jim, if we do have time at the end there, we'd like to get the Smart Scope presentation in. So to that end, we're going to cross our fingers, and I ask everybody to come up, that's going to come up and present information on their images, to please speak quickly. And to that end, I want to introduce you to a friend. This here's Captain Hook, and he don't have a lot of time for lollygagging and long-winded speeches. So if you see me reaching for this, well, laddies and lassies, take heed. Your time's almost at hand. All right. Next slide, please. There we go. So our program tonight, I'm going to be really brief here. Al Scott's going to come up. Gary Boyle's going to do our usual Ottawa skies, and then as a departure, because we really don't know how long the Transit of Venus stuff is going to take, we're going to do that right after Gary. Depending on where we are, and now that we've lost a few minutes with our technical glitches, we may break in the middle of the observations and carry on afterwards. Otherwise, we'll try to finish them before the break. Obviously, then we'll go to Brian, and he's going to show us that video on the moon sketching. And then Simon has an awesome talk for us tonight. I've seen the slides, and I'm just blown away. I think you're going to love this. And then we'll talk a little bit about public outreach, and hopefully, Jim, we'll get the Smart Scope update too, right? Okay, next. We have a few Ottawa Centre members in the news. Unfortunately, this should have been up last month. It wasn't. Sorry about that, Mike Wirtz, wherever you are. But Mike Wirth's fabulous lunar images in the June issue, the June page of the calendar there. And as usual, Mike's work is exquisite. Then we have these three very serious-looking scientist-y guys. They're, with their very serious-looking glasses. There. What publication was this? I'm sorry. It was Celebrate Summer, but what is that?
Citizen magazine.
Magazine in the Citizen. There. Thank you. So talking about the Venus Transit as well. And then again from Mike Wirth's in the current issue, the July-August issue of Sky News, we have another one of his highly detailed lunar pictures. Awesome piece of work. Our own Rolf Meyer has a piece in there as well. He's got the Mars shot in for April the 2nd. Fabulous detail on a very wimpy Mars. This opposition. Good, nice work, Rolf. And Peter and Deborah Saravola with their shot of the partial lunar solar eclipse that we had taken from their plane at several thousand feet, at 8,500 feet there. So a rather unique observation platform. So. Congratulations all around. All right, good. All right, without any further ado, Al. And I'll keep this at hand.
All right, I guess we better get going. Can you cue up a video? So I'm going to start with a video, actually. And it's kind of interesting. We're focusing on the sun. We're talking about gamma ray bursts on the sun. So this is the gamma ray sky as observed from a satellite. There's the Vela pulsar, which is typically the brightest thing in the gamma ray sky. And there's a solar flare that was observed by this new satellite. At one point, the sun was the brightest object in the gamma ray sky. This satellite was able to actually measure the outburst from a flare and localize it to the disk of the sun right there, the Fermi satellite. And so this is the first time we've actually observed and been able to localize and tell that these gamma rays are coming from solar flares and from the magnetic fields. And so what they're thinking is that the energy in the magnetic fields associated with the flare is actually causing a gamma ray burst. And then I think there's a little bit of a description of the physics coming up pretty soon. So you have these magnetic field lines, they're tightly coiled, and what happens is a magnetic reconnection event where some of the magnetic field lines release a whole bunch of energy when they cross. That causes the flare. It accelerates protons, and the protons can collide. So you have a proton colliding with another proton, or a gas atom. And what happens is a pion is created. The pion then immediately decays or quickly decays into two gamma rays, which are extremely high energy photons, basically, similar to the light we see, except able to create nuclear activation of nuclei. So let's go to the next one, please. I don't know if we have a pointer here tonight. Or...
It's in front of the monitor.
Thank you.
Center button.
Okay. So continuing on the theme of solar outbursts, on March 8th there was a coronal mass ejection that propelled a class X5 solar flare in our direction. The solar flare classes are like a Richter scale for solar flare energy, so they're logarithmic. And the upper curve here is from the SABRE satellite, which is monitoring infrared emissions in nitrous oxide and carbon dioxide in the nitric oxide and carbon dioxide in the atmosphere, which are actually these are actually up in the thermosphere, and they play a key role in cooling the thermosphere. So you can see that if there's energy being deposited in the ionosphere and the thermosphere, it'll come out in the infrared signature in emission from these compounds in our upper atmosphere. So on a 3-day period from March 8th to March 10th, the thermosphere absorbed 26 billion kilowatts of hours of energy from the sun and re-radiated 95% of that back into space, which you can see here is this spike in the curve. This is both good and bad. What happens is that it actually puffs up the thermosphere like a big marshmallow, and it actually affects satellites that are orbiting in low Earth orbit, and it can actually cause a drag on satellites. This has the good effect of cleaning debris out of the low Earth atmosphere, because we've been putting so much up there that it's actually dangerous for satellites. Has the bad effect that it also creates drag on useful satellites and uses up their fuel quicker. So it's a problem for people that operate satellites. And the interesting thing about solar flares is that they follow what's called a power law. There's basically a logarithmic log-log graph here on intensity of solar flares along this axis and frequency along this axis. And you can see as they get more intense, they also get less frequent. And it's really not clear what the limit to this log-log curve is or how big these events can actually be. Astronomers have seen extremely large events in distant stars, but they think that the sun is a relatively well-behaved star that doesn't have these extremely large events. Most of them are associated with binaries that are close orbiting and interacting fields between two objects. The most powerful flare ever observed was the first one to be observed on September 1st of 1859, called the Solar Storm of 1859, or the Carrington event. It was actually visible to the naked eye on the sun in white light and produced stunning auroras down to tropical latitudes. It also set telegraph systems on fire because of the geomagnetically induced currents and the long stretches of wire. It's interesting what we could think of might happen if one of these big ones happened again with all of our electronics and satellites in orbit right now. On March 13th, 1989, geomagnetically induced currents from an X-15 flare actually caused a blackout, blew up transmission stations in Hydro-Quebec and also a transformer in New Jersey. 6 million people were affected. In November of 2003, we were just missed by an X-45 class flare. But imagine what would have happened if it had hit us. Anyways, something interesting to think about. And our systems aren't all that stable. The next, I'll go to the next one. I'm having trouble with this.
Everything's screwing up tonight.
The next slide, and my last one, so I'll try to be quick. Archaeoastronomy. This is also associated with highly energetic events from stars, but not necessarily just our sun. It was triggered by an article, a science paper, just over, scientists were measuring actually carbon-14 in tree rings, and they found a peak of carbon-14 just over 1,200 years ago, around the year 774. And you can see it over here. This is the measurement of the carbon-14, and then suddenly in 1 year, or 2 years, or 3 years maybe, probably just 1 year, it goes up significantly and then drops back down. Carbon-14 is actually created in our atmosphere from energetic particles, gamma rays, for example. It's a radioactive isotope with a half-life of about 50,000 years. And it's incorporated into living things, and it's used to date living things. But the problem is, we don't know of any particular event that happened in 774, 75 that could have caused this burst of radiation to hit us. The only two real contenders that we know about would be a nearby supernova or an extreme solar flare event. Now, this is basically 20 times the annual rate of creation of carbon-14 in 1 year. So if that happened in a single super flare, it would have likely destroyed the ozone layer. The event, we've measured up to a 75% depletion just from large flares in recent history in the ozone layer, but it's temporary. So I did a little bit of Google searching around the time of 774 to see if there was anything that you could find in the historical records, anything online. And there's the Anglo-Saxon Chronicle describing the first Battle of Otford in 775 AD, said, "This year also appeared in the heavens a red crucifix after sunset." So possibly a supernova-associated observation, or possibly just some sort of fanciful description of atmospheric phenomena like aurora. The thing is, nobody records a supernova around 775 AD. People have looked, actually, this is a record of nitrate concentration in ice cores in Greenland. And people can actually measure these peaks, which are associated with radiation bathing the Earth. What they think these events are, they actually correlate with events. They think this is the 1859 flare, and we've got supernova Kepler, supernova Tycho, and the supernova of 1185, which are all historically recorded events. And then there's this one here, which happened about the year 1300, assuming the record is linear. So it's wrong for the tree ring source, but you'd think someone would have observed a supernova in that year. Well, here's a new supernova remnant that was discovered 700 light years away from Earth, and actually superimposed on the Vela supernova remnant. It's called Vela Junior. And based on the size of this, they think it happened right around 1300, but nobody observed it. Interesting, because the Tycho supernova was magnitude -4, and it was 7,000 light years away. So some interesting things that can be learned from looking at historical records on Earth. It's called the field of archaeoastronomy, and there's still things to be discovered. We don't know what caused this, so the jury's still out. Thank you.
Thank you, Al. All right, next up, Gary Boyle, Ottawa skies. What's happening, Gary?
Not much.
Not much.
For once it's clear, but it's just so damn hot. Edit out the word damn, please. So welcome to, hope everyone had a happy Canada Day. Here we are, the second half of 2012. We had summer solstice that was on June 20th. The great thing is that now the nights are beginning to get a little longer. And with that, we can enjoy the warmer conditions and observe the nighttime sky. Next slide, please. And first thing in the morning is, if you can recall back to March of this year when we had the beautiful Venus-Jupiter show in the western sky, now we have the opposite, where Venus is in the lower sky. This is in the morning before sunrise, and the bright star Aldebaran, Venus, Jupiter, and the Pleiades. So, and this is for tomorrow morning, so it's a great digital moment. Next slide. So here we have at night, we have the summer triangle, which consists of Deneb, Vega, and Altair, and these are the distances in light years. Altair and Deneb are about the same brightness, but you can see that Deneb is about 200 times further away. So the summer triangle, very visible, Cygnus the swan, the wings in flight, the very long neck. And first we'll look at Albireo. Next slide. Albireo. Hey, there's Albireo. Albireo is a beautiful binary star. Two very contrasting colors, yellow and green, sometimes yellow and purple. It depends on the person's eyesight. Distance is 385 and 376 light years away. It's beautiful in any telescope. The colors are vivid. It's really one of the targets of any nighttime observation, especially star parties. Next slide, please. The next constellation after Vega, 25 light years away, we have Lyra the Harp. And the spectacular object in Lyra is called the Ring Nebula, or M57. And M57 is a planetary nebula. A planetary nebula is really a star that has pretty well is old age now. It's used up all its energy, and instead of becoming a supernova when it blows up, it casts off its outer shell. Well, these stars get so large that gravity cannot even hold itself together. So now all the very, very ends of the gas begin to fluff off and form this nice ring or shell around the star. So this is what we're looking at, 2,300 light years away. The central star is about 14th magnitude, pretty faint. But even the disk itself is 8.8. But still, it's another spectacle in the sky to see a smoke ring or a Homer Simpson donut, as I tell the kids. Next slide. And coming down to Altair, the last star of the summer triangle, we have beautiful open cluster of stars, M11, or called the Wild Duck. It's 6,000 light years away. It's just about naked eye from very dark conditions. And it's just a gorgeous open cluster of stars that has a very bright star in the middle, which is a foreground star. In fact, it's in front of the cluster. It's only a lineup, so it doesn't belong to the cluster itself. So again, a great digital photographic moment and just a treasure in the eyepiece. Next slide. Here we have some homework and the challenge for this month. I'll put a challenge down to find Pluto. I mean, Joe Bonner last year came to my observatory and he found Pluto, no problem, just to verify it, but it's actually passing below M25. So this would be your guide to find Pluto throughout the month. So if someone can take some photographs or sketches for next month, that'll be great. So that's the challenge. Of course, you will win nothing, just a great round of applause. Next slide. And just to save time, can anyone name the 8 planets in order? My very educated mother just served us nachos. Next slide. And there we have the moon. Next month, I put in blue because the second full moon of next month is the blue moon. So on the 1st, we're going to get the sturgeon moon, and on the 31st, the gray moon. The moon does not turn blue. It's just a term given to the second full moon in the same month. And speaking about month, see you next month. Thanks.
Thanks, Gary. Okay. Transit of Venus observation reports. Thing we've been talking about. Chris and I are going to change seats here for a second, and he's going to talk to you about the happenings here at the museum. What I would ask, just to expedite things, is if you see your name on that list, if you would line up on that side of the auditorium, so that we can get you up in fairly quick order. Okay, I'd appreciate that. Will save us a bit of time. Thank you.
This is not working either.
No, this is the night where everything is going wrong technically. Even our advancer doesn't work.
Okay.
Next slide, please.
Here we go.
So before we start into the actual observations of the transit of Venus, we thought we'd start and put it in context with the event that happened here at the museum. As you know, the museum has a lot of public events and usually invites us to participate with telescope support and educators. And on a really good event that's well publicized by the museum, I think that we've been getting upwards in the 300 to 500 people. This event happened during the workday before a dinner, so expected turnout may not be that fantastic. And we hit 2,000 people. We knew we had 1,500 the eclipse glasses free to give away, and we ran out. So mind-boggling the interest that the Venus transit seems to have garnered with people, and a great job by the museum of then promoting it. So this gives you a hint of some of the crowds that we were dealing with at all times out in the field here. Next, please. What impressed me during the event, and it was really Peter Heyman, one of the organizers, who pushed that the various volunteers bring different techniques for viewing. And these next slides I'll go through very quickly now, just show you the variety of things that people were doing to observe. Obviously it started with the eclipse glasses that we gave out in large quantity, not just the 1,500 here, but hundreds and hundreds were given out before the event. So everyone who wanted had that chance. Not that they were the best optically for viewing. Next. But they were very popular and well used. Next. Now here's a new technique I wouldn't have thought of. An iPhone camera through solar eclipse glasses. People were trying everything. Next. This worked out really well. We always talk about it for solar observing, but welding glass was something that we could pass around, had many of them, and people had a great view, far better than the eclipse glasses. And you can see by the fingerprints on the glass just how well used it was. Bill kept juggling 3 or 4 of these welding glasses with people. Next. Again, another technique, photographing through welding glass, though I think the welding glasses missed covering the lens fully. Next. Another technique I've never thought of, an iPhone camera through binoculars. People were trying everything. Next. We had eyepiece projection. Next. As well as just traditional telescopes with the full variety of solar filters. And I thought this was fun. I just happened to snap this picture myself and catch one of the audience trying to take a picture. She then came to me and said, can I send you the picture I took, which is next. Then she brought her camera, just a complete amateur, never observed through a telescope, pointed the camera down to the eyepiece, and next, and gets that kind of image. Not fantastic, but a lot of people were not only observing with their eye, but would come up to our telescopes with their cameras and get amazingly good results. Next. And then for another technique, you're seeing there beside the telescope the case of my camera, which is the backdrop for, next, laptop. What you're looking there, obviously, in the screen of the laptop, Transit of Venus, live from SmartScope. It's been a long time since we've displayed with SmartScope, but Jim Maxwell and his group put a lot of effort to get things working at even a basic level, and here we are broadcasting live over the internet and picking it up on my laptop in the field of the museum, and people were getting to see it that way. Next, this may be a bit of a technical challenge because we're having video problems tonight as well as many other things, but Paul's going to try to display a brief portion of the live broadcast from SmartScope.
You will try. Where am I going?
Oh,
It doesn't want to.
doesn't want to do it. Well, I'll squeeze it in between talks or at the end of the talks later.
Sorry about that.
Then if we can go to the next one. And then the museum put together their own little video of the event. This is a bit of a teaser. We're going to show you that image in much more detail later. That was not taken through any one of these telescopes. They're going to intersperse photography of the event here with some incredible NASA imaging that we'll show you in more detail later. Again, it shows you the number of people crowding through the place. Interspersed with this NASA imagery.
I thought that was SmartScope.
The other amazing thing that I don't mind rubbing in to the members here who drove long distances to get clear skies, I think we set the record for clear skies right here at the museum. We were clouded out with 15 minutes left to go. Other than that, it was completely clear. It was a beautiful event, so that again helped in having the huge crowd there. Next, or I think that's it. Oh, no, Here, 4 members, but in particular, wanted to point out from left to right, Peter Heyman, Melanie Hall, and Stephen McIntyre, who were the 3 organizers together with myself, and then Jimmy Book, who's a real steady volunteer that's at most of our events. And next and last, a thank you to then all the members who did come out, particularly on a weekday during work hours. It was badly needed with the number of people we had. Thank you.
Okay, give it a quick try there. It's your computer, you know how to do it, hopefully. Oh, there we go, see? So this is just a piece, I've sped it up. There was they actually recorded some of the stuff from the Smart Scope there that Chris was showing live in the field there, and I just captured it off the website there, and I've sped it up considerably. This was about 5 minutes worth of the video, and I've compressed it down to about 30 seconds there. But you can see that, yeah, she's up and running, and I think that bodes well for things to come from the Smart Scope. Here we go. Good. Glad we got that in. Thank you. All right. Roman, who now resides in Australia, has sent us some images there. Of course, he got a different perspective of the transit than we did there, since he was on the other side of the planet. And what he did was something that Chris mentioned there. He took a series of very simple images, I think with a Nikon Coolpix 9000 and through solar glasses. And there we go. We'll just buzz through those quickly there. But yeah, you can see that Venus is on the wrong side of the disk from our point of view, right? That's because he's south of the equator. Here we go. Yeah, very innovative techniques, as Chris was saying. People are using everything but the kitchen sink. All right, Brian McCullough. Here we go.
My wife and I had a date with our daughter from the last transit of Venus from 2004. And can we back to the first? Oh, sorry.
Sorry if that advanced. I don't have that in.
Oh, okay. I probably stepped on something. Yeah, so when we observed as a family the transit in 2004, our daughter Emily, who's now studying astrophysics, she's a PhD candidate at Western University in London, she said, we'll go down there for the transit for 2012. So we went down there, so that's her boyfriend Chad Bennett on the left, and there's Bridget and me, and we had a number of instruments we were observing with, but Emily does it in style. We'll go to the next one, please. Emily and Chad set up a picnic. So we came with a formal invitation at our hotel room, and Bridget and I went down. There was a cold chicken and all the drinks. Emily even brought her china teacups. All right? And this transit happened on Emily's 28th birthday, so I saw that flying by. I said, look, Emily, I got you a balloon for your birthday. So, but anyway, all right?
Surprise.
Oh, right. Emily won the, I don't know if anybody had seen this before, but she won the Ramsey Award. It's for teaching, for a Northern Science teaching award. So she's done a fair bit of work up in the Arctic. So we were pretty pleased about that. A little bit of solar projection. You can just see the dot of Venus on that card there. I'm on the left. I think I must have been wearing my beret. And that's Chad holding the paper. And we were talking about different ways of observing. We'll go to the next one, please. Chad took a pair of the glasses, cut them apart, taped them across the front of his telescope, and observed that way. And this is, it's hard with the light here. This is as the sun is setting with Venus there, going down past the power lines. And then this is the next shot that's about the next to the very last one that I got, just as the sun is disappearing below the trees. I think that's it. All right.
Great. Thanks, Brian. Bob Olson? Bob? Is Bob here? No?
That makes it quick.
That makes it very quick. These are from Bob. That was from Bob. Okay, you go.
Okay. Since I'm out in the West End, I thought I'd go down to the Diefenbunker site. And I thought I'd see quite a few of our members there, but as it was, there were only a couple there. And so I wasn't really prepared to use my telescope there at all, because it's just a little one. But since there was hardly anybody there, I thought I'd try my old projection method. So you can see there, you can see the disk of the sun, down at the far left there on the small telescope. And the disk is quite large. It's about almost 4 inches, so it's quite large. And I was surprised how well it worked. Go to the next. Okay, and here, this one, you can just see the Venus has just entered the solar disk there. And down on the bottom there, because it covers, you can see the edge of the shade there. It's at the edge of the field of the scope, because at that magnification, I had to keep adjusting the position fairly frequently, and it kind of got away on me there a little bit. If you go to the next one. Okay, now here you can see it further on, and you can see this quite clearly, the sunspots, but what you can also see are some scratches. And unfortunately, since I wasn't really thinking far enough ahead, I never checked my screen to see how perfect it was. So, but it's fairly clear what is scratches and what's sunspots, because the scratches are quite thin. And then I just have one other shot there, and then the clouds started moving in. Just one comment, but using this method, one of the advantages is that you don't actually have to look at the sun. All you do is has a polar axis on the stand, so you just approximately align it up, and then all you do is you watch the shadow of your scope and sort of minimize the shadow until the image of the sun appears on your screen, so you never actually need to have glasses or anything. I tried also taking a couple pictures with the filter and just with my camera. Yeah, it turned out, but it wasn't anything as good as this.
Great. Thank you. Gary Boyle.
Well, I was very pleased to see the extreme example of an annular eclipse. The sun was only 4% covered. But yeah, here we have Venus, many sunspots. In fact, my day really began early because I was on CTV live twice that day, first at 10 to 7 in the morning at the race back for the noontime show. And then we left around 2 o'clock to go down to Kingston because we weren't sure about weather conditions, which I'm really glad it turned out well over here. A lot of people did get to see it. So just with an 8-inch Doddsonian reflector I built in 1977 with a Botter filter in the front, just a series of 50 images stacked together, many beautiful sunspots. In fact, this is about Earth size. So memorable, and I do have images of both transits, and couldn't have been any better. Had a super day. In fact, it rained halfway up to Ottawa, so it was just truly amazing. I'm glad everyone really enjoyed the site. Thanks.
You had another image.
Oh, I'm back. Then on the 14th, we had sunspot 11,505 and 11,504. Beautiful, just a series of spots. Did this from my observatory with my 10-inch Alex 400. Great. Thanks. Any more? No.
Tim?
Yeah. I gotta run. I gotta go up and do cloud gazing in a minute.
Oh, okay.
Yeah, this is actually a photograph from a handheld camera, just with a Botter solar filter over the top of it. I did most of my imaging retinally. Next, what do we got? Oh yes, this is the egress. Since this was taken down from a beach, the seeing conditions weren't that great, and quite frankly, I didn't really care.
Tell them where you were.
Oh, yeah, right, I forgot. The previous one was taken from this one's taken from the Visitor Information Station in Mauna Kea, which was an absolute zoo that was just crowded beyond belief, and again, nobody really cared. And this one was taken from Waikoloa Beach because we were worried about possible clouds on Mauna Kea. We had just ducked a snowstorm that day, which had gone north of the island. There we go.
Nope.
A snowstorm? Yes, a snowstorm. Yeah, that's right. We just ducked it. It just went north of the island. That's mid-transit, photographed from, I believe it was a 4-inch teleview on the summit. And the winds up there are running about 60 miles an hour, so we didn't really set up a lot of telescopes.
Can you explain what we're looking at? It's a strange setup.
This is called a sun funnel. And what this is it's a piece of rear projection material from a rear projection TV hooked up to a plain ordinary funnel put over an eyepiece. So it's an eyepiece projection gizmo. And there's a lot of these. Yeah, there's another one right there. I have just finished seeing first and second, and I'm rather pleased with myself, as one might notice. Cheesy grin notwithstanding. So there we have it. That's up at the Mauna Kea Visitors Information Station, and man, that was a busy day up there. There was a parking lot all the way up the access road. And I do believe...
How high the telescope was pointing compared to us looking longer.
Yeah, well, actually, the elevation of the sun there at start of transit was 87 degrees. And even with 50-mile-an-hour winds, it was crystal clear. The seeing was absolutely spectacularly perfect. Yeah, it was a good trip. Fun. And I got to go outside and cloud gaze.
Thanks, Tim. Tony Peterson? Is Tony here tonight? We weren't sure whether he was coming. Okay, I'll just quickly address that. Obviously, Tony's setup there. He was, I think he was up on, up near Foymount there. Next, please. And he sent us a sequence of images, rather nice there. You can just see at the top, just past contact 1. Nice definition on the sunspots. There we go. Thank you. We're pointerless today. And just presume very, very close to contact 2. And of course, well into the transit, probably not far from the end from our point of view. For those of us that didn't get a chance to go to Hawaii, Tim, he's already gone. And yes, a bit of artistic cloud work as well. Great. Thank you. Thank you, Tony. John, come on up.
We also didn't want to take a chance on the weather here.
Use the microphone.
Oh, yeah, sure. Instead of taking a chance and staying here in Ottawa, we just drove a few hours to just a little bit north of Bon Echo Park. It's an abandoned airfield. So we have Paul there and Ivan Juger and his son, Nicholas. That's Paul's fancy setup. Next, please. To the left, that's my setup. I had a 35 millimeter camera with a 200 millimeter zoom and a 2x extender. So I was supposed to get 400 millimeters, but in all the excitement, I nudged the telephoto ring and ended up with 320, but I didn't discover it until I was finished. Overall, it went really great. I took over 800 images. It was so easy. What else? I used like a homemade filter assembly with a powder film, which I got from Paul. Thanks, Paul.
Oh, you're welcome.
Okay, so this is just some of the images from the sequence. You can see at the top just a tiny entry and then, self-explanatory. And then the day was really great, but it ended like in a spectacular sunset.
Great.
Thank you.
Thank you, John. Deborah and Peter are, there you are, Deborah. Come on up.
Yeah, Peter wouldn't come up because he's having a bad hair day.
Yeah, I know that problem too. Yeah.
Well, this is kind of like a little mini partial eclipse. I thought this was really cool. We went out to the Carp Library, the Diefenbunker area, because we wanted to get out into the country, enjoy the peaceful scenery out there, and it was a fantastic evening. Next slide. This is Peter. He had a setup of a 4-inch Orion with a Canon 20D snapping away. Took a lot of photos in this position, and at the end of the day, I noticed he had a pretty good burn across his forehead, and I said we called it the transit tan. But we had another, I had my little Tau 4-inch Newtonian with a homemade Botter filter on there, just to look at and to show people that came by. A lot of people came by, some kids and families. And next slide. This is probably maximum transit before the clouds started rolling in. It's probably one of the better shots. Peter complained that it's not that sharp because there's a lot of, what do you call it, mirror slap with the Canon. You might do it differently, but we'll have to wait, I don't know, how many years?
108.
108 years to do it again. Okay, next slide. Yeah, at one point he actually caught a jet coming in from the west, flying into Ottawa. You can see it down there. Join the field. It was kind of fun to catch that. You can even almost see the contrail there too. Yeah, next. And that's Hugo there. I think Hugo was up here a few minutes ago. I think, Hugo, you were even wearing the same shirt. So we had a police officer come by and check things out, and she seemed to really enjoy the scene as well. It was a lot of fun.
Did she shoot the sun, or was it just you guys?
The next slide. Yeah, here come the clouds, but it kind of made for some interesting shots. This looks like kind of almost extraterrestrial, like a planet of some kind, like Mars or something. The next one. I had my Canon 60D with a long 200 millimeter lens, and I was hoping to get a horizon shot without a filter, like we did with the Eclipse. But I was able to do that with the Eclipse because we had a really hazy air mass. This time it was a northerly air mass, and it was really clear and bright all the way down to the horizon. So it was really oversaturated. But if you look close, can you see it? You can actually see it there. So I actually managed to capture in one shot. And a nice little sunset. Next. And this is the last one, a parting shot just before, this is taken also with the Peter scope, just before it disappeared for good. Thanks.
Great.
Oh, I have another shot. Yeah, a couple of weeks ago, I was out in my backyard and I looked up and I saw the beautiful solar halo. And it's caused by cirrus clouds in the high upper atmosphere. And this one lasted hours and hours, all day long. So I was out barefoot on the road with this lamppost completely overhead and burning my feet taking this shot, but I think it turned out pretty good. That's cool.
Very nice.
Thanks.
Very nice, Deborah. All right. Joe Bonner?
So I was also one of the people that traveled for the event. We actually checked the weather forecast, and Kingston was looking better than Ottawa, so we took it down there just to be on the safe side. And this is one of the better shots I got. And looking at it later, we were trying to figure out, is this a Jupiter-sized phoenix coming out of the sun on its way to devour the Earth? Or maybe it was that seagull that was after the French fry in the parking lot, not sure. But I'm betting, I think it might be the seagull. Next slide, please. This is one of the last shots we got. We had pretty good weather in Kingston. We had no clouds at all until the very end of the event. These clouds are actually just barely above the tree line, so we were about to lose it to the trees anyway, but I thought the clouds made a nice kind of dramatic contrast there, so I snapped off a few of those. Next slide, please. And there's the happy traveling crew. We have Pat Kavanaugh on the left, Gary Boyle, and myself. There's Gary's, the Dob he mentioned, is his homemade Dob from 1977, and my Meade LX90. Okay, next slide, please. Is this the video?
Yes.
Yes. So I caught another transit on the summer solstice, and that slowed down to about half speed.
It's a loop.
Is it going in a loop? There it is again. So I used the Cal Sky website and got notifications of ISS transiting either the moon or the sun, and I've tried a number of times to catch it, and it's a pretty narrow corridor even when you're close, and this is probably my fourth attempt in the last 2 years, and I actually caught it just from my driveway. I didn't even have to travel to get it, which I was pretty pleased about. And yeah, let's move on to the next one, please. I got a couple stills. So this is an image basically I took. I stacked about, I think this was about 20 images, with the last image stacked being one of the frames with the ISS in there. And I was a little disappointed that there wasn't too much sunspot activity. There was a little bit there, of course, but would have been a little more dramatic with a few sunspots, but oh well. You take what you can get. And this is a composite shot I made of basically taking the video itself. The transit took something like 0.8 seconds. It was pretty quick. And in fact, I didn't even know I had it. In fact, if I play back the video at home with the audio, I'm watching the clock and saying, and I can hear myself saying, "Oh no, it's passed. I missed it. But when I got back into the house and could see it without the glare of the sun in my eyes on my little tiny DSLR screen, there it was, 0.8 seconds going across, and this is a composite of about 10 of those frames. And lastly, this is the same shot you saw before, but I just cropped a bit out and zoomed in. It turned out pretty well. I'm quite pleased. I was pretty lucky to get it. So I think that's my last one. Thank you.
Nice work. Nice. Okay, Rolf. Rolf's got a collection for us.
Okay, I guess these are these are all starting to look pretty much the same, aren't they? So anyway, let's. What? It's not working. Okay. All right. Good enough. Okay. Next. Okay. So this is how we observed the event. About 20 people bicycled over, and I had a screen set up, and it was a huge bright image projected with a 17.5-inch Dobsonian telescope, and afterwards we had cake. The seeing was just spectacular. The sunspots and the disk of Venus were extremely sharp, even projected onto the screen like this. Okay, next. This is with a 6-inch telescope and Canon 5D. Yeah, looks just like all the others that were shown. Next. Okay, so this is, these were all full disk images, so I just cropped the area around Venus for this. As you can see, there really was no black drop that we were all waiting for. This was, let's see, one of these. I think this one, no, well, actually, I've got another one that's pretty close. I think this one may have been the closest to the actual second contact time. Next. Okay, so this is a very interesting phenomenon. I only got this on one shot. This was about 2 minutes before second contact, and I really had to enhance this. This is not the black drop effect, but really what you have here is, if you look very carefully, there's actually sunlight being bent by Venus atmosphere, and it completes the circle there. So you can only see that just before second contact. Next. Okay, and there we go, last shot, just before it went behind the clouds. Okay, I didn't advance it there. Okay, so you think these ISS transits of the sun are pretty rare. So the first one that was shown was June 20th. This was June 27th from my observatory. I guess these things must happen all the time. Now this was with ISS at about 1536 kilometers, and so it was very distant compared to how it could be. It could be about 4 times closer. Now remarkably, there was one 5 days later at my observatory, but it was cloudy, unfortunately, and it would have been a lot closer and more spectacular. Next, Saturn. Not particularly great that night. Next, this is Mars, getting pretty small now. This was around 7 arc seconds. It's now around 6.5 arc seconds. And next. Okay, so this is my first deep sky picture with this new camera. And gee, unfortunately, these podium lights make for a very poor contrast, but over here you'd be able to see IC 4623 as well. And this is everybody's first astrophoto, I guess, with the telescope M51. And next is M81 and M82. Pardon?
How long was the exposure?
I think it was about an hour and a half. I can tell you more after the meeting, I guess. And 6-inch refractor, yes. And next, finally, spectacular rainbow. And that's it.
Nope.
Oh, there's more. Oh, there's more. Yes, there is more. So this is not observation. Just a reminder that we're having the picnic this year on August 11th. I suppose we'll have another reminder next month. So that will be also in our yard. And oh, this is how. Oh, I don't know how much there is here, but this is, I guess, so when you first come in, you'll turn right where that arrow is. So you immediately turn right, and then you just follow the road up the hill. And, oh, there's a map. So just remember that. Well, I think if you just you'll probably find it somehow. Is that it?
That's it.
Oh, okay.
Thanks, Rolf. Next two shots, Rob Lavoie sent those to me for inclusion tonight. I wanted to give you a chance to show this. He got something that looks close to the backdrop. Again, it's a psychological camera, depending on your point of view. And his following shot did a nice job, Rob, on the annotation of the sunspots that were there. There were numerous. For those of you that observed through a scope there, you certainly got to see a lot of variety, including the transit itself. And Rob shot those with a 5-inch Maksutov Cassegrain and a Canon D1000. Okay, thanks, Rob. Of course, I had to get in a couple myself there, as John mentioned. We were up at the Nirvana site because it looked like that was going to be the one of the best places for it. As it turned out, everybody got a good look, which I was so thrilled about because you don't get a second shot at this. Nirvana was good. We like everybody else had periodic clouds. Probably about 10% of the time we were clouded out, but when it was clear, it was very clear. So we all got an amazing number of shots in. Next one, please. There's just a sequence that I put together showing the one frame before the actual transit, and this one I managed to get right at the transit. Of course, you're not going to see anything because just starting at that point in time, you can just see it slowly nudging in there. And this one I managed to bag about 10 seconds after second contact. Unfortunately, as Murphy would have it, we did have clouds at the moment of second contact. This was shot as soon as the clouds cleared. So, but no complaints there. It was great. As a couple of people have mentioned, when it was clear, it was really clear, and that was a real bonus. Next. So like a few other folks there, I did a few artistic shots there, but I was really hoping to get the really clear sky, because what my real interest in doing this transit was to get some really high res stuff. And so most of my time and my effort had been spent to optimize my equipment for high-res imaging. And next one, please. That's a product of that imaging system there. You can see there's a lot of detail actually on the surface of the sun as well. And this is a stack from a movie sequence there. So it's about 72 images stacked together, which gives it nice clarity and stuff. And you know what? I got something that I'm not sure what it is yet. I've sent Doug George a copy of this image there to pick his very knowledgeable brains on this subject. But you'll see what I mean. The next one, please. Okay, so there's my shot. And there's a shot I picked up from the NASA Solar Dynamics Observatory, operating at the same scale, oddly enough, as my telescope. I was operating with a 150 millimeter Mac Cass. Thousand Oaks solar filter, full color imaging, so 390 to 750 nanometers. The NASA satellite using that particular band is a narrow band at 671 nanometers, both at about 1 arcsecond resolution. What I was really curious about and what I was really hoping to get was this ring of light around the planet. Now, I've heard conflicting stories about this, and I'm certainly open to anybody that has knowledge about this. And even on the internet, I haven't gotten a clear explanation of this. So obviously, the SDO is in orbit above the Earth. It's immune to the obscuration of our atmosphere and the vagaries of the atmosphere, and it recorded this halo of light. Me with my little 6-inch, I also recorded the same halo. These were actually these two images were taken at almost the same time. Obviously, this one was a little bit earlier into the transit there. So the question is, and this is the question I've posed to Doug George. I'll give you an update once I've had a chance to confer with him. What is that ring? Is that an imaging artifact? Is that atmosphere, the atmosphere of Venus being illuminated by the light of the sun coming through? Is it a combination of both? Is it pixel bleeding because of the extreme contrast of the dark sphere of Venus against the light sphere of the sun? Answer is I'm not really sure. I haven't heard a definitive answer one way or another, but I was just thrilled that I managed to get something that looked like that because I'd seen a few from the last transit. And remember, the last transit 8 years ago was the first transit where anybody at any time had ever done any imaging. I mean, the one prior to that was just at the dawn of photography. So 8 years ago, this was all very, very new stuff. And there were some images like this as well. And there was some debate whether it was an atmospheric or an imaging of artifact. So stay tuned. I'll give you an update as soon as I got one. But I was just thrilled that we got very, very stable skies and clear enough to do that type of imaging from the ground. So NASA with its $1 billion budget, me with my considerably smaller budget. So there we go. I'm thrilled. It was great.
Paul?
Yes?
One clue, to go back to the image,
Sure.
one clue that might give some idea as to what could be happening.
Okay.
Just compare what's happening at the interface between the dark disk and the immediate adjacent bright area with the appearance at the solar limb, where you have a similar thing happening. Even if you discount limb darkening, I'm seeing what looks like a little bit of that deeper orange fringe adjacent to the dark
Yep.
black. So it
Yeah.
could be something to do with
With just the fact that there's such a contrast. Although with the edge of the solar disk, again, I'm not sure. It's like the limb darkening gets pretty extreme when you get down really, really close to the margins. So again, is that just the the logarithmic decrease, or is that actually an imaging artifact? I really don't know the answer, Glenn, but that's a good observation, and you can also see that on the Solar Dynamic Observatory's image there as well, where you've got a little bit of that artifact or effect going on there. So, yeah, interesting stuff. Good stuff. And I got a parting shot as well. This one, I think it was very similar to what Deborah was trying to do there, although this one I left the solar filter on and was able to pick up details. You can actually even see some of the sunspots there, a couple of the brighter ones there. And then I just cranked the hell out of the image there to pick up the cloud mass, which was very, very dim on the image because of the solar filtering. So all in all, a super event, and I am so thrilled that everybody got a good view of it. It's it's not very often where we get an opportunity on a global basis to stop and think about things other than what's just on the ground in front of us there, and look up and share something that has truly a global appeal. So we were very lucky. All right. A couple of objects for you that are non-transit related. Now for a quick switch, right? I tried to do Hoag's object last month through a smaller telescope, and I showed you it was a very disappointing image. So I used one of my medium-sized telescopes, and this is, again, these next four shots, my friend Jason Coley hasn't asked for his Canon 60DA back yet, so I'm still in a testing phase, which thrills me no end. It's a beautiful camera. If you want to talk to me about the ultimate DSLR for astrophotography, come talk to me afterwards. This thing's a work of art. Anyway, very, very sensitive. So I've got four shots that are deep sky. This is the first one. This is Hoag's object. As I mentioned, it was the challenge object. This is a very, very peculiar ring galaxy that's 600 million light years from Earth. So picture that. I mean, the light from that galaxy left that galaxy before dinosaurs were crawling on our Earth. And to pick that up with I used a 7.5-inch Max Sutov there, and that is a stack of 4 10-minute images with the Canon 60DA. So I was really thrilled to get that. I'm hoping to do much longer sequence with my 11-inch and pump up the scale by about a factor of 3 there. So I'm waiting for that opportunity. It's one of my high priority targets. Next. This was a really quick shot. This is one, Glenn, when you were out there doing some imaging with this there as well. This was a shot that was already well into dawn light. It's a single image of M3, again with that camera. So you can see there's a lot of blue already in the sky. That was a 90-second exposure of M13. So yeah, very impressive camera. Next one, M51. Again, same with the Canon 60DA. This is through the 7.5-inch Max Sutov Newtonian. This is a stack of 4 10-minute images there, and because the 60DA has the filter appropriate for astronomy, you're getting some good light, red light along the arms there. So yeah, very impressive camera there. And I think the last one I have is that one. And again, that's through the Maksutov Newtonian there. That's a single shot with the Canon 60DA.
The Orion one?
That's no, that's the Canon. The Mac. Yes, it's the Skywatcher.
190.
Yeah, 190 Maksutov Maksutov Newtonian, and it's an f5.26. So optically, it's reasonably fast. The optics on it are beautiful. You get round stars right to the edges there. And as I say, that camera performs wonderfully. 10 minutes into these exposures at 800 ISO, and there's virtually no noise on them. And so again, a single exposure with some processing there, but lovely sensitivity in hydrogen alpha and indeed across the color spectrum. So very pleased with that. 2 thumbs up on that work from Canon. I think that's it from me, right?
Yep. And
Great.
that's finished with a bang.
Thank you. Wonderful. Our last contributor is this. You've got to watch this. If you haven't seen this, this is awesome. Have we got video or audio? No? I don't know. So, since we don't have audio, I'll narrate. This is, in fact, you'll recognize this. This particular band is the one I was comparing my own image to. This is from the Solar Dynamics Observatory, which runs about, I think it's 4 different telescopes in 4 different narrow band regions there to pick up different features from the atmosphere of the sun. So basically it followed the entire transit there, and what you're seeing here is a collection from NASA. Look at that. That's spectacular. Just spectacular. Hydrogen alpha there. So what they're doing is they showed you a close-up there, and then they'll show you transit at each band across the disk of the sun. Mm-hmm. So is it limb darkening, or is it an imaging artifact, or is it both? Right? Yeah. And again, it's not in that. In some of these bands, there's no evidence of that. So I find that really odd. Just some stunning imagery though from the SDO. And again, as I said, I mean, even 8 years ago, we didn't have the same hardware in orbit that we have now. NASA's dedicated some considerable resources into putting these solar observatories into orbit so that we get a continual picture of what's happening with our nearest star there. And so really what we're seeing is stuff that's unique. Nobody in our species has ever seen this stuff before because it's never been done before. You've got hydrogen alpha, you've got ultraviolet, you've got visible, all narrowband stuff. It's just lovely. And of course, nice. You can see the activity from the sunspot regions there. If you watch the sun very closely to it, you get a sense of its turning. There you go. Yeah, not too long to it. Is 105 or 108? 105. I stand corrected. I stand corrected. Sorry, Deborah. Well, that's actually better because I told you 108, right? Yeah. So you just bought 3 years. So here we go. So to conclude our observation reports, these are non Venus transit reports. We have 3 other contributors. Our first and one and only Paul Commission. It does? Okay, wonderful. First one for Paul, please. You just told me to work. Yeah, there we go.
Thank you, Glenn. This is 609, NGC 609 in Cassiopeia. It's also known as King 3, and it's an 11th magnitude 3-minute type of very small but very interesting type of open cluster. It's about 13,000 light years away, and it has about 77 stars in it. The reason I'm showing it is I wanted to tell people you see the exposure is only 20 seconds. With a lot of these bright type of open clusters, you can take what I call a snapshot. You don't need to spend hours on end running around, bending over, and all this kind of. Take a thing in 30 seconds. If you have a large enough a scope, in 30 seconds, and there you are. And this reaches about 15th, 16th magnitude. So you've got the thing completely covered. So next, please. This is also an open cluster in Cassiopeia. It's NGC 654. This is Malot 9, and it's a distance of a little closer, about 6,700 light years away. The number of stars, I think, in this thing is a little less, but the age is about 14 billion years, or a million years. This is a little younger, I think, than the other cluster. Next, please. This is an interesting thing. When I started to take this picture, I didn't realize this at the time. This is NGC 4088, but it's ARP 18. ARP are all these disfigured galaxies, and the reason that it's an ARP is that it's a spiral with detached segment. You notice there at the top left there's a detached segment, so that is why ARP put that in his collection. You notice it's kind of an S shape. It's a peculiar shape. ARP galaxies are all sort of, they're not standard. This is not a standard thing. The magnitude is not too bad. It's 11.2, so you could see it in about a 4 or 5 inch telescope. The size is about 5 minutes, and the absolute magnitude is -20, which means it's a fairly large thing. But you notice over, Paul, point to the left, sort of, there's another galaxy. Now that one is 17.6. So that's a much smaller one. It's one of these PGC things. But sometimes, so this picture goes down to about 18th magnitude, and the exposure was 10 minutes. So, but hopefully I won't be showing too many more black and whites. I'm going to buy myself a colored camera. You won't have to look at this whole stuff.
That's great, Paul. Wonderful. All right. I think we have Glenn LeDrew. Advances there.
Yeah, I'm younger than Paul, but I can't bellow quite as loud, so I'm going to make use of the microphone. These series of photos you're going to see were taken in about mid-June from Paul's sort of country hacienda west of Almont. And I just slapped my Malin cam. It's just basically like a glorified video camera, but optimized for astro imaging. So it's not a high-resolution camera. It's about 330,000 pixels, as opposed to, where you've got multi-megapixel cameras that are used by many people. But it's very sensitive. These exposures, well, this one here was only 15 seconds. The following ones were all 30 seconds. And this is an old open cluster in Lyra. In fact, it's a challenge object in the Observer's Handbook. It's NGC 6791. Now, I've seen it on excellent nights with just a little 7x35 binocular. It's a very ghostly little haze right at the limit of detection. The brightest stars in this cluster are 14th magnitude. And I haven't bothered to figure out what the limit is that I'm seeing in these exposures, but it's probably about 16th or so magnitude in 15 to 30 second exposures. And these are just single frames, no real processing done at all. In some of them you'll be able to pick up a little bit of amplifier glow like you get up in the upper left corner there. That's just from the way the readout amplifier is right next to the CCD, and it generates a little bit of heat, and that registers as noise or glow. The next image is the planetary nebula M27, or the hourglass, or the apple core, as it's commonly known. The camera is very good at picking up the colors of the oxygen-3 emission, which appear greenish, and the hydrogen alpha, which appears reddish. The scale of these images, by the way, I think it's roughly about the diameter of the moon that would fit in these images, just to give an idea. the image scale covered. And if I didn't mention it, it was a 12-inch telescope, and it was using a 0.5 focal reducer. So the instrument was working at a pretty fast f2.5, which is partly why the exposures could be kept so short, even though the sky was very dark. I like to use an exposure that will actually show a bit of sky glow, where you can see a non-black sky. That way you see the faintest details in nebulosities and such. The next image is the Deerlick Galaxy, or NGC 7331 in Pegasus. Several other galaxies are in attendance nearby, probably more likely as a little group farther behind 7331 itself. The dimmest galaxy you see there, and I don't have a pointer, but it's the...
Center button.
Oh, sorry. This little guy here is nearly a 16th magnitude galaxy. So you can see then that it's detecting substantially fainter than that. Next is another galaxy, sometimes called the Fireworks Galaxy, NGC 6946, kind of on the border between Cepheus and Cygnus. This galaxy, as far as I recall, has had the highest number of recorded supernova events since we've been detecting these things in other external galaxies. Next, this is the Iris Nebula, NGC 7023 in Cepheus. This is a reflection nebula, one of the brightest of its kind in the sky. It's visible in moderate-sized binoculars. 60, 70 millimeter binoculars show as just a little fuzz surrounding this relatively bright star that's reflecting around. And in the image, you can kind of see here and over here, down below, these kind of regions that appear somewhat star-poor. These are just denser parts of the dark molecular cloud, and we're just seeing here where the a star that formed inside it is kind of blowing out a bubble. And interestingly, here is an almost completely transparent section right through the cloud. There's dark cloud material all around, basically, but here we've got a nice little hole punched right through for whatever reason. Next, we move farther north up in Cepheus, Cassiopeia, I guess it is actually. This is the Bubble Nebula, NGC 7635, I think the number is. This is a recently excavated cavity around a Wolf-Rayet star, and you can't quite see the full ring. The resolution is not high enough here because the image scale is not so great, and so on, but it records the dimmer outer parts of the nebulosity quite well. And next we have another Wolf-Rayet remnant, the famous Crescent, NGC 6888 in Cygnus, not far from the star Gamma Cygni, the middle of the Northern Cross. And here is the central star, whose outer layers have been puffed off in a sort of a, think of it as kind of between a planetary nebula and a supernova explosion, somewhere on that continuum in terms of violence. And the shock as this material is flying through interstellar space, hitting surrounding material, is causing the gas to fluoresce. The excitation just due to the shock of slamming into the surrounding medium.
Does that camera have a Bayer filter on it?
A Bayer filter? Well, there are little artifacts with the coloration of some stars. Some of them appear a bit yellowish, and some might have a bit of a magenta cast. Part of it has to do with not fully sampling the star size, so you end up with them falling on a pixel that has a particular color mask on it, and then that will dominate for the color of those stars. If I wanted to get rid of that, well, I guess there are things I could perhaps do in after processing, or I could stack lots of images, or shoot at much larger image scale. But this kind of imaging, I'm just sort of getting my feet wet in this. It used to be old film photography years ago. And do I have another one after this? Oh, yes, of course. The Veil Nebula, a supernova remnant, is much too large to fit in the field of view with the telescope I was using. So I shot a half a dozen exposures, sampling it from the north side on the right, working my way down to the southern parts in the lower left. And you'll notice what happens. This was a go-to Dobsonian telescope, so it's not polar aligned. And as a result, as you track the sky, field rotation causes the object to rotate in the field if you stay on it long enough. And because this was over a period of about 20 minutes, you can see a systematic rotation of the images as I tracked from one end of the object to the other. That's why the images have a little bit of a canted orientation with respect to each other. And that is it.
Nice work, Glenn. Okay, and finally we have Jacob von Koris.
Hi, here I have an image of the Leo triplet consisting of Messier 65, Messier 66, and I believe it's NDC 3628, if I remember right. This was taken at Irvine Lake Airstrip, or Nirvana's, just north of Bon Echo, consisting of 2 hours of exposure last May. It would have been nice to have gotten more exposure, but Leo was getting too low on the horizon by that point. This is my shot from my Skywatcher Equinox 80 at prime focus with my Canon 1000D. This is with the camera wasn't modified at the time.
So it's a DSLR?
Yeah, it's a DSLR, one shot.
That's an amazing picture.
You have an auto guide?
Yes, this was auto-guided with the Ryan Starshoot auto-guider with this Ryan Short Tube 80 at an effective 800mm focal length.
Amazing. That's a brilliant picture.
Thank you. Next slide. This is an image taken after I modified my camera with my Beta hydrogen alpha filter at 7 nanometers. This was taken in my backyard here in Ottawa, but the Beta filter cuts out most of the light pollution since this was taken near the new moon a few weeks ago. The exposure was a bunch of 15-minute exposures with, resulting in a total of 4.25 hours of exposure at hydrogen alpha, producing this image of the dumbbell. I was quite happy with the detail that I got in the nebula. The entire nebula is filled out almost to the point of saturation in the core, with some of the dimmer hydrogen alpha nebula showing up around the outer region. Yes. This is an image I took quite a while ago. I actually showed it a few months ago at the April meeting before I modified my camera. So you can see the hydrogen alpha region isn't as bright as you may see in a modified camera. So what I wanted to do is, with the original image, combine it with this image to produce an enhanced image. Next slide. This is the red channel of the image you just saw previously. As you can see, it's quite noisy, which is typical of a red image. And the hydrogen alpha data isn't nearly as good as the original hydrogen alpha, but the stars there's many more stars because it's the full red spectrum, and I wanted to keep those. So the next image, please. I combined the two to produce this. As you can see, there is a gradient between where I combined it, but in the next image, you'll see that it doesn't really show up to produce an image with much more hydrogen alpha. The hydrogen alphas come out more from the hydrogen alpha image, while the stars around the edge are preserved, and the gradient doesn't show up nearly as much since there's much more data put into there.
Nice.
Thank you.
Great. Very nice work, Jacob. Very nice. All right. Simon, you're going to love this. I saw the slides and just, yeah. Take it away, Simon. And I'll try not to use the cap on you.
All righty. Let's see if I can. Oh, good. All righty. You know, science is a funny thing. Sometimes it's too difficult or too expensive to get to study the real thing. So you end up studying analogies. You end up studying analogies instead, things that you think resemble the real thing, and see if you can draw reasonable conclusions about the real thing from that. Now, I got lots of air miles saved up, and the trouble is they're no good to get me to Mars. But this past spring, they did get me to a beach in Brittany in western France. And what I saw there made me think of Mars. In short, I saw what I think are analogues of surface processes that have sculpted the Martian surface in its early geological history. And that's what I want to talk about tonight. Now, much like cigarette packages and movies with adult content, I have to warn you about analogues. As a professional geologist, I've done quite a bit of laboratory modeling on how rocks might behave when they get squished, for example, by colliding continents. They're great fun. That's to say, these analog models. They're great fun, and they do stimulate the thought processes. But you must never lose track of the fact that there's a huge difference between reproducing the same end result and simulating the natural processes that actually got you there in nature. Technically, this is known as the problem of causality. Just because you turned A into B doesn't guarantee that you did it the way that nature did when you do it in the laboratory. So it's really important that you keep this in mind while we talk about models and analogues of what may or may not really occur in nature. Next one, please, Chris. Okay, having taken care of my insurance policy, let's cut to the chase. Here's a typical image of one kind of Martian topography, canyons. Most planetary geologists would suggest that they were carved by water. Next one, please, Chris. And here's another image of the same phenomenon, and it points out part of the problem with this hypothesis. Both the main canyon, this thing here, and the lateral alcoves coming off the side are blind. They simply stop at steep cliffs. This raises a critical question. If they were carved by water, where did the water come from? On Earth, your average valley is carved by river systems that have typical branching patterns as tributary valleys coalesce progressively to feed into the main valley, but not here. Next one, please, Chris. The previous images showed you the upstream end of typical Martian canyons. This is the downstream end looking back upstream. This is where whatever was eroded to form the canyon has spilled out of the canyon mouth to form what's technically referred to as an outwash plain. That's this stuff here coming out of the canyon. Now, keep this blind canyon and outwash plain topography in mind, because we're going to see quite a bit of it in the next few slides. Next one, please, Chris. And this is where we're going to see it. This is a very ordinary sandy beach in Brittany, western France, where I spent quite a bit of time this past spring. It's nothing special. Many of you have probably seen beaches like this wherever you've been spending holiday time. But I wonder if you took a good look at those sandy beaches. So, let's take a good look at this one. First, you notice how flat it is. There really isn't much of a slope. And secondly, this is important, notice how wet it is. Tens of meters from the sea, and it's still soaking wet. This is going to turn out to be very important in my Martian analog proposal. Next one, please, Chris. So here I am, I'm standing close to the surf zone, my back is to the sea, I'm looking inland towards the sand dunes that form relatively high ground compared to the beach, and there are two things that I want you to notice. Firstly, notice the dry sand. That's this stuff here, the really nice clear stuff there. Oops, sorry. That's this here. There we go. That's the dunes, and then it's this here is the dry sand. And the more extensive wet sand in the foreground here. What does this tell us? Next one, please, Chris. Well, this wet sand tells us that the sand beneath the surface is waterlogged, and that the upper limit of the waterlogged sand intersects the surface slope of the beach a long way inland from the sea. Here's the surface slope of the beach. The sea is out here. This is where the dunes would be. This is the dry sand near the dunes. And this dotted line here is the top of the waterlogged sand, and it intersects here with the surface, so this would all be the wet sand. And this is what's called the upper limit of the water table. Next one, please, Chris. The second thing that I want you to note. Yep, good. The second thing that I want you to note is the streakiness in the wet sand. You can see it best in the foreground here, but this streakiness goes right the way back up to the limit of the wet sand. If we walk inland towards the dry sand, but still within the wet sand, we can see that the streakiness of the wet sand has an inland limit above which the sand is perfectly featureless. So we'll see that in just a minute when I think on the next slide. Next one, please, Chris. There we go. Here's the featureless sand. The dry sand would be up here, and then here's the streakiness. So here we are within about a meter of where the water table comes to the surface of the beach, and where surface water starts to flow down the very shallow slope of the beach with just enough energy to start to erode very shallow channels in the sand. And you can see these very shallow channels here. Next one, please, Chris. Now, it may be just coincidence, but here on the left, here, is a very similar channel pattern on the Martian surface that appears to start from nowhere, just like the beach features. Nothing, and then streakiness. nothing, and then streakiness in channels. Note, of course, that the Martian pattern is at the scale of kilometers to tens of kilometers, in contrast to the beach channels, which are at the scale of centimeters. Next one, please, Chris. Okay, back to the beach. Unlike rivers and streams, these channels are everywhere. Instead of the water localizing in narrow valleys, it flows like a huge sheet, uniformly about a few millimeters deep. While it doesn't concentrate in valleys, some of these anastomosing channels are longer and more continuous than others. Watch this one here, for example, and another one here, and then there's another one here, and there's one over here doing the same kind of thing. So what? Why get excited about this? Next one, please, Chris. This is why. On the left is a Martian landscape, kilometers across, with what I think is an analogous pattern of channels to those which we've seen already in the beach sand. Here, even the long channels here, the same as this long channel here. Very different scale. Very different scale. Next one, please, Chris. And if we look more closely at the beach sand, we can see that the surface water has carved anastomosing channels that isolate elliptical islands, like this one here, or this one here, or even this one here. And those elliptical islands, they contain older, even finer scale channels which are preserved internally. You can see them here, you can see them there. Next one, please, Chris. And if we get still closer, we can see that the surface water in the anastomosing channels, and you can actually see the water is actually flowing in those channels as I take the photographs. It's actually managed to carve cliffs. You see them here, here, which stand several millimeters high. If the width of these channels on this beach was really kilometers across, as it would be in the Martian example, these vertical cliffs would be the equivalent of tens to hundreds of meters in height. Next one, please, Chris. So here we are, we're still at the beach. As the erosion in the channels proceeds, it progressively isolates elliptical islands of high-standing sand, and you can see them nicely defined here, even better than in the previous slide. Next one, please. And here, on the left, is a Martian example.
Aren't your labels reversed here? Sorry, Simon, but aren't your labels?
Nope. Sorry, pardon, you're right. This one here, I've got my labels in the wrong place. This is Mars, that's the beach.
They're not on Mars. Who was there? Kilroy.
Chris, have you been playing with this, Chris? All right, take me for a mug. Hang on a minute. You wait. There's yet you will see some footprints in a minute. All righty. I guess I asked for that one, didn't I? Huh? All righty. Whereabouts am I here? Okay, there we go. What the hell with it? My labels were in the right place.
There's only certain speakers we can do this to yet.
Okay. All right. Here we go. So, as I suggest, on the left is a Martian example of something that looks very similar to our beach channels. And I'm going to suggest that the two are perhaps analogous. Next one, please. Here's a second example of what I would suggest is the same analogy. Now, there are so many examples I could show, but these two will suffice to get the point across here. Next one, please, Chris. Now, how do we know that these channels and islands are really erosional? This is key. Well, on the beach, we can actually see the relics of older beach ripples. See these ripples here? We can actually see them within the islands and trace them, in fact, from one sand island to the next. The ripples have clearly been truncated as the shape of the islands was determined by erosion, by flowing surface water that is still flowing in these channels, by the way, as I'm taking these pictures. Next one, please, Chris. Let me check, see what's been done to my image here. Okay, fine. And here on the left is a Martian analog with internal ridges that can be traced from one topographic island to the next. These internal ridges here within the islands can be traced from one island to the next. Remember, in all the cases that I'm showing you here, the Martian examples are very different in scale from the beach pictures. Kilometers to tens of kilometers on the one hand, centimeters to maybe a half a meter on the other. Next one, please, Chris. So let's go to just downslope from where the water table intersects the beach surface and the erosional features first begin to form. I'm checking my image. Now, apart from the dog paw prints, there are paw prints in this one. They're supposed to be there. Definitely not Martian analogues, at least not yet. What do we see? I see a trough right there. I see a trough with a blind upper end that appears to be the source of a very different sand. This sand is quite granular here compared with the sand at the very surface. Very different kind of sand, a sand that forms what looks like a downstream outwash plain and had to be derived from underground. It's not this sand, it's another layer of sand underneath that's been washed out here. Next one, please, Chris. This was not a random one-off feature. These blind troughs appear to be characteristic of the beach close to the point where the erosional features first appear. No erosional features, they begin to appear, and the troughs begin to appear immediately. Next one, please. And here you can start to see how they are indeed blind. They're like blind canyons, and they're bounded by lateral cliffs. You can see them quite nicely picked out by the shadow here. Every one of them has these nice high-standing cliffs. Next one, please, Chris. These are what geomorphologists, or you might call them physical geographers, refer to as box canyons. And in this particular case, you can clearly see that the canyon floor has a few millimeters of water flowing in it. This one here very nicely, and you can see the water flowing through there too. While the plateau into which the canyon is being carved, that's this thing up here, including the broken glass, is dry. Clearly the water in the canyon is coming out of the ground. It's groundwater, and it represents the level of the water table at the moment I took the photograph. Next one, please, Chris. Here you can see how the flow of the groundwater onto the canyon floor at the base of the canyon cliffs is leading to collapse of the canyon walls. You can see it nicely here. You can see it even more nicely here. This is not erosion by surface water, as in a river valley. This is what geomorphologists refer to as sapping. It's as the water comes out of the ground, it weakens the cliff and the cliff collapses. Next one, please, Chris. Well, here at a very different scale, potentially is a potential Martian analog of the beach box canyons. This is probably several tens of kilometers across at the very least. This image that I found from NASA didn't have a scale on it. As for the beach examples, the canyon is blind, and there are no tributaries which would have fed surface water into the canyon to account for the erosional topography. Next one, please, Chris. Here's another Martian example with a somewhat different morphology. This one's nice and spoon-shaped. And next one, please, Chris. And yet another example, just to press home the point that these blind canyons are very common on the Martian surface. Here's the top of the blind canyon here, and the canyon would go out this way. Next one, please, Chris. We've skipped one. Have we? Oh, no. Next one, please, Chris. There. Hang on a sec, let me just check where that image is definitely out of sequence. Okay, we'll pass on this one. Next one. There we go. Okay, I'm good. Okay, so back to the beach, where I came across this beautiful example of multiple blind box canyons, which were feeding into, which represent tributaries to this major channel here. Again, you see the major channel is full of water. Next one, please. And I'd like to suggest that this example over here is an analogous feature on Mars at the scale of multiple kilometers. Compare this, any one of these, with this feeding into the channel.
You see the flow lines in that one.
Yes, indeed. Yes, you can see the flow lines here. And in fact, when you're looking down into, through the water, you can see the flow lines in the beach example too. Next one, please, Chris. There we go. Okay, so these blind canyons on the beach look like the larger examples on Mars, but what does that tell us about whether the processes that formed them were similar? Well, here, back at the beach, plus paw prints and footprints, there are footprints, I believe they're mine. You can see the blind box canyon feeding into an outwash plain. There's the blind box canyon feeding into that outwash plain there. And at the mouth of the canyon, you can see what appear to be blocks of the canyon wall, right there, that have slumped onto the outwash plain. Next one, please, Chris. Okay, I'm just checking that one there is definitely out of sequence. Okay, what we'll do, Chris, we'll jump back to that one. Move forward one. There we go. Actually, no, we've got a number of them are out of sequence on this one. Move forward one more, just so I can see what's going on here. Okay, that's this one. Move back. Okay, let's wing this. Move back one. There we go. Okay, so this is a close-up example of that slumping occurring. Let's move to the next one. Alrighty, we're talking about the process here of forming these. So these blind box canyons forming by this sapping process feed into these long curved channels. Next one. And I think that this here on the left is a Martian equivalent of this kind of long channel. And I believe if we go to the next slide, this was simply to show you that not only is it my interpretation that this slumping here is due to the sapping, I actually came across this process occurring. This slump here actually occurred as I was stepping across the channel. Next one, please. And here, this Martian example here, this is in the long curved channel. This is indeed, I think, the same kind of slumping we're seeing in this long curved channel here on the Martian surface. Let's see how we're doing. Next one, please, Chris. Okay. Yeah, these have come out of sequence here, but that's okay. And here's yet another example of that slumping. You can see the rubble here at the base of the steep cliff and this fan here. So, yes, we'll work with that. Next one, please. Good. Okay, we're back in sequence here. So back to the beach once more. As I've already mentioned, the blind box canyons commonly feed into outwash plains. And where several canyons are closely spaced, those outwash plains can be quite extensive. And in fact, they can be quite impressive. Let's go to the next one. Here's what we were just looking at in the last slide, but we're looking upstream now towards the box canyons. And you'll notice how the broad curvilinear channels filled with shallow water separating the large elliptical islands with steeply eroded cliffs. You'll notice the islands and you'll notice the cliffs and the streakiness here in the larger curved channels on the floors. Next one, please. I think that is directly analogous. That previous beach example is a direct analog for this Martian case, which is hundreds of kilometers across, where broad curvilinear channels spill out of the heavily cratered Martian highlands onto the relatively smooth northern plains. The northern plains are here to the north, which is in the lower part of the image, and this is the heavily cratered terrain area to the south. Next one, please, Chris.
Process to give the appearance that there's water on Mars?
No, that's the image straight off of the NASA website. Whether they've played with it to give that image impression, I don't know. I would hope not, because
the increased reflectance.
I know it really looks as though there's water in there. I've got to tell you that when you actually see this on the web, there is no indication in the text that's what has actually been done. And in fact, I'm looking at this right now down here. That actually is not a NASA image. That's actually an image which is, you're probably right, it has actually been treated.
Is that near the polar cap?
No. This is probably very, very close to the eastern end of the Great Martian Valley. Valles Marineris. Next one, please, Chris. Okay, so while we're at it, let's compare this iconic, well-known iconic image of the erosional islands on Mars with features of that French beach. You can see the beach up here and the famous image here.
And the erosional islands similar to these in the Ottawa River, just a bit downstream of downtown. I forget the name of them. There's these sort of little almond-shaped islands that are...
Yes, but the thing is that they are associated with primarily with channeled flowing water in a river system.
Okay.
You're talking about Kettle Island?
Yes.
Yeah.
And next one, please, Chris. And here again, a similar kind of thing, of the iconic Martian image, which you can compare with what we see on the beach. Now, they may not be identical in every way, but I think you get the point. The processes we see on the beach make us think about how similar features may have formed on Mars. Next one, please, Chris. Remember this Martian image that I showed near the beginning of the talk? Well, how do you think it compares with the image of what I would suggest is an analogous location with respect to the box canyons on the beach, looking back up towards the box canyons, and here looking into the main canyon system? Next slide, please. So here's a last look at the beach, looking towards the sea and the surf zone. And the take-home message from this photo is that the outwash plains with their flowing water and the active erosion of the cliffs at the upstream ends of the box canyons on the beach have nothing to do with wave and surf activity in the ocean itself. Everything we've looked at here is related to the release of groundwater and its arrival at the surface of the beach, and I would suggest the surface of Mars. The important point here is that when we're talking analogues, the important thing is once you've got the groundwater in the sand, the analog model begins to run. I'm not suggesting for a minute that a Martian ocean put groundwater into the ground of Mars. What the water is doing there is a different kettle of fish altogether, different set of processes altogether. Now, next one, please, Chris. I love analog modeling. It's really very exciting. However, you must not get carried away. Analogies between models and reality do not automatically mean that the models accurately simulate natural processes that led to what we see, for example, on the surface of Mars today. Philosophically, this is the problem of causality, where there are lots of possible ways of getting to an end result, but which one represents reality? Just because I can show you analogues of Mars on a beach doesn't mean I've proven anything. Let's look very briefly at just two flaws, two errors, if you will, in my analogy. First, if you look at a real Martian canyon from far enough away, it looks very smooth. Next one, please, Chris. But if you get inside them at high resolution, there's a roughness in the beach models simply do not reproduce. Secondly, even if you accept that the general geometry and relative dimensions of the beach and the Martian box canyons are similar, there's a major scaling error in the analogies that I've drawn for you here. If you scale the canyons, channels, and cliffs on the beach up to the scale of the real features on Mars, our beach sand grains should represent boulders the size of houses and larger. And this is clearly not what we observe on Mars. So if for this reason alone, you should be somewhat wary of taking my presentation too literally. However, the beauty and the purpose of analog modeling is that it enables us to envisage possibilities that may not otherwise have occurred to us, and it enables us to push our critical evaluation of what we're looking at, those ideas, to much further forward. Last slide, please, Chris. So let me close by asking and answering the following question. Do I think that the beach examples are reasonable analogues of the kinds of processes that have occurred in the distant geological history of Mars? Yes. Do they answer all of our questions? Unlikely. Do they point us in the right direction? Absolutely. Thanks for listening, and a happy year of the solar system to you.
Very nice, Simon. Thank you.
Did we have some questions?
Oh, only momentarily. We are over 10, but we'll have a couple. Okay.
What's your theory on where the water came from? Could there have been a large watery comet impact event that delivered the water, and then because of it being a smaller planet, it then evaporated off into space, leaving those channels in the runoff from the event?
No, you don't need it. The bottom line is we know that Mars in its early history, prior to 3.8 billion years ago, still had a magnetic field. That magnetic field would have protected its atmosphere. Its atmosphere would then have protected any water on the surface. And there's a lot of evidence that around, in the early history of Mars, there most certainly was water, there was most certainly was also glaciation. Thick glaciers are moved over Mars, and we can see them preserved. The chances are that what actually happened here is that as Mars began losing its water, it would have lost it in two directions. As it lost its magnetic field and lost its atmosphere, the water would have then disappeared off the top of the atmosphere without protection from the solar wind. The other thing is that water, as on Earth, would actually sink into the ground. And we're all, as Canadians, aware of permafrost. The most recent results from orbiting probes around Mars tell us that there is, even today, there is permafrost in the ground, and it is hundreds of meters in thickness, potentially up to a kilometer or so. All it takes, and this is what people are thinking about, is volcanic activity within the Martian crust, which then introduces local heat sources, melts the water, and that's how you produce your groundwater.
So Simon, are we really talking about oceans?
Are we talking about?
Oceans? Are we talking about oceans?
Yes, I think the evidence is stacked up really nicely, and I gave a talk on this last year. I think they really are managing to show that the southern limit of the northern plains, which is the flat, younger surface of Mars, that really does look as though it is the floor of an ocean.
Well, the floor of our oceans here on Earth resemble what you're showing us here tonight.
No, actually, the floors of our oceans don't. There are erosional canyons. There's no doubt about it in the edges of the continental shelf, but there are no continental shelves that we can see that exist on Mars, because the floor of the ocean on Mars is very, very different geologically to the floor of the oceans on the Earth.
Thank you.
I didn't get hooked off.
No. You were close, though. You were close. All right. Just a couple of slides in closing. We are running, actually, surprisingly, only a few minutes over. Again, I apologize for the talks that had to get moved to subsequent months there. But as you saw, we had a ton of images there, and I wanted people to get a chance to share their experience for that rather unique event of the Transit of Venus. So recent events, obviously, the Transit of Venus was very successful. Hundreds of visitors at chapters with the OAFs or so as well. Information sessions in numerous schools, including Notre Dame High. Notice of, oh yes, we had the June 16th, the dark sky public stargazing at the public library, can't speak anymore, 14 scopes and lots of visitors. And then of course Canada Day celebrations at Cecil Morrison Park there. There was some scoping to be done there as well. Next slide. Coming events. On now until July the 29th. If you remember from last year, the Cube Gallery is holding a similar event, the Festival of the Night Sky there, with artistic works from various artists, and they're also going to have a downtown public star party where I believe, again, they've managed to get, yes, they have managed to get the lights turned out for one night. So that's in a week from now, July the 12th there. So if you want to go down and try to see stargazing from the city, check it out there as well. And all through there, they'll have sessions. I think it was on the 3rd and the 5th. They also have, actually the 5th. Is that was yesterday, right? Yeah. That was yesterday. Anyway, go down and check out the event if you want. There's also a poster there. I think you can just ping on the Cube Gallery website there to get a complete list of the events. They'll have several speakers there as well. It is an all-month affair for them. Okay, next one, please. July the 13th. So next Friday, the July 13th public star party at the Defen Bunker there from 9 till 1 a.m. and we'll cross our fingers for clear skies. Next, coming events, the Ottawa Lumiere Festival at New Eden Park, August the 18th, and National Science and Tech Week, the Science Fun Fest, a rather well-attended event on October the 14th. So a little bit downrange there. And yes, I guess we have some status posted on our website there as well. So in closing, Estelle's pick of the month. If you're looking for a good read, Book of the Cosmos. Estelle, I did see you around there, so
around today.
Yeah, I assume that we're going to have that. Thank you. And next, Just a reminder too that we coffee and membership info and such are not available this month. There, sorry about that. And Al Scott is around. I don't know if he's still trying to get rid of telescopes there, but go and see Al if you'd like. Rest of the museum is closed, and drinks and snacks over at Kelsey's afterwards. And we're only 10 minutes over. Wonderful. We had triple X audience. 91. Sorry about that. 91. And again, thank you for all the people on the list that contributed images and helped organize the events. So our last slide, a reminder that next month's meeting is not the first Friday. It is, in fact, the second Friday, August the 10th at 8 p.m. Again, sorry about that. Scheduling conflict with the museum there. So we do what we can. But give me a shout if you have any ideas for presentations and stuff. Also, if you have anything that you would like to donate for our prizes, I did get some donations today, but Mother Hubbard's cupboard is running a little bare. So if you have anything that you're really not using and you want to just pass along there, bring it along next meeting, and we'll gladly take it off your hands. Thanks for coming tonight, and thanks to all the contributors for the wonderful images. Hope you have a great July, and we'll see you next month. Thank you.
In early March 2012, a powerful X-5.4 flare erupted on the Sun. The blast was observed by the fleet of spacecraft dedicated to monitoring our star, plus one unlikely addition, NASA's Fermi Gamma Ray Space Telescope. For Fermi, which detects high-energy gamma rays, the Sun is almost never the brightest, steady source in the sky. That distinction is reserved for the Vela pulsar. But on March 7th, the Sun outshone everything else Fermi could see. Thanks to the big flare, the Sun had become the brightest object in the gamma-ray sky. Due to the keen angular resolution of Fermi's Large Area Telescope, for the first time, scientists were able to narrow down the position of the high-energy gamma-ray emission to a part of the Sun's disk. This gives scientists greater confidence that the gamma rays come from the same region as the solar flare seen in other wavelengths. During this event, the LAT detected the highest energy light ever recorded from a solar flare. The gamma rays peaked at 4 billion electron volts, or 2 billion times the energy of visible light. With Fermi recording high-energy gamma-ray emission for 20 hours after the event, the March 7th flare also set a duration record. Several mechanisms are behind this gamma-ray activity. Flares are thought to arise when strong magnetic fields undergo a process called reconnection and release pent-up energy. A sudden blast accelerates charged particles, some of which leave the Sun, while others are driven toward its visible surface. Many of these accelerated particles are protons. When they collide with gas in the Sun's atmosphere or surface, the interaction creates a particle called a pion, which quickly decays into 2 gamma rays. These observations herald Fermi's arrival as a solar observatory, a powerful new tool for understanding the Sun as it approaches its maximum period of activity.